So we have to take a little side journey into physics. So we're going to talk about light. The interaction of light with atoms helped scientists to understand what was going on inside the atom. So what is light? Light is a form of electromagnetic radiation. Radiation always sounds scary, but there's a lot of radiation that is not dangerous at all. Light is not matter. We discussed matter earlier. Matter is anything that has mass and occupies space. Light does not have mass, and light does not occupy space. Light is not matter. It's a form of energy. It's a form of energy that travels through space at a constant speed. That speed is known as the speed of light. So that speed is 3 times 10 to the 8th meters per second, which might not mean very much to you. That's 186,000 miles in a second. Light is very, very fast. Light has properties of both waves and particles, and that's part of the disturbing stuff that we're going to have to talk about. So here we have a picture of water droplets falling into the surface of the water. And we've all seen this. The water droplets, as they hit, they cause waves on the surface of the water. And those waves are going to be concentric circles that move out away from the source. Right? So the water surface is disturbed and the waves move out. These waves are carrying energy as they move through the water. They don't look very energetic, but if you've ever stood in the surf at the ocean and had waves crash over you, is there energy in those waves? Heck yeah. They can knock you down, right? So there's energy in the waves. Waves carry energy. Light behaves in many ways like waves on water. So this is an illustration of a light wave, and so it's a sine wave, and it has crests or peaks, and it has troughs. So it goes up and down and up and down and up and down as it's traveling through space. So we can quantify the light in a couple of different ways. We can look at the wavelength, the length of the wave, and that's given the symbol lambda. It's a Greek lowercase l. It kind of looks like an upside down Y. For visible light, the light that we can see, this wavelength determines the color that our eyes perceive. So if we're seeing blue light or red light, it's because the wavelength of the light is different. If we take white light, light from an incandescent light bulb or light from the sun, and run it through a prism, a piece of glass, it will separate into a rainbow. This happens with little drops of water in the atmosphere, and that's why we see rainbows when it rains, or if you get just in the right place and you look through sprinklers, you can see rainbows. Or sometimes I have a glass light fixture by my front door, and when the sun hits it, there's little rainbows all over the room. It's kind of neat. Only happens if it's clean, though. So it's separated. And it separates into these different colors because the different wavelengths of light, as they go through this prism, are bent different amounts. So it separates based on the wavelength. And this is called a spectrum, and this is a continuous spectrum. The colors vary continually from red to violet, and there's no gaps. Here's a picture of a woman standing in the surf. Her shirt is red. Her shirt appears red to us because the material of the shirt is reflecting red light and it's absorbing the other colors of light. So light with the wavelength characteristic of red is coming and entering our eyes, and our brain interprets energy of that wavelength as the color red. Another way of measuring waves is the frequency. And this symbol is the Greek letter nu, which looks unfortunately like a lowercase v, but it's got a little curve in it. Frequency is the number of cycles or the number of crests that pass through a stationary point in 1 second. So this woman standing in the surf, there are waves coming in. Now they're not going to come in more than 1 per second, but you could measure the frequency by counting how many waves hit me in 10 minutes. And that would be a frequency. For light, we measure it in the number of crests or waves in 1 second. The wavelength and the frequency are inversely related. If one is long, the other is short, and that's because light always travels at the same speed. So if we think about that, so here's my little person. I'm not an artist. So the wavelength is the distance between two crests of the wave. Which of these waves has a longer wavelength? This one's longer, right? It's a longer wavelength. This is a shorter wavelength. These waves are traveling at the same speed. So if this person counts the waves that are passing, let's call them A and B. Which one is going to hit you more frequently? Wave A or wave B? B. They're moving at the same speed. This is going to go bang, 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 bang. And this one's going to go bang, 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 right? It's because they're traveling at the same speed. If the wavelength is large, then the frequency is small. So this top one has a large wavelength and it has a low frequency. The other one has a short wavelength, but a high frequency. Okay? So that's light behaving as a wave. Light can also be viewed as a stream of particles. You've probably heard the word photon if you've ever watched any Star Trek shows of any type. Photon torpedoes, right? They're always talking about those. Well, a photon is an actual thing. A photon is a particle of light, a piece of light. It's a single packet of light energy. And that's a little hard to think about. It's like saying, I'll have 2 pieces of milk. What? Milk doesn't come in pieces, right? Actually, it does, but they're so tiny that you can't even think about them. But light can be thought of as having particles. The amount of energy that's carried in that packet of light depends on the wavelength. So a shorter wavelength is going to have more energy than a long wavelength. Another way to say that is light waves carry more energy if their crests are closer together. So high frequency, shorter wavelength, that's higher energy. So back to this person with the waves. If these are ocean waves coming in, they're going to pound on you, right? Which is going to be harder to withstand? Which is going to be more pounding, more energy coming against you? Wave A or wave B? B. Because this is hitting you again and again and again. This is short wavelength, high frequency, also high energy. This one is going to hit you less vigorously because you have a little time to recover in between, right? And this talking about the waves and hitting you, this is just to help you remember the relationships here. It's not actually how light is. It's not hitting things like waves crashing, but the idea works. When I look at these 2 waves, this one looks more energetic to me, doesn't it? It looks like it's jumping up and down. It's really excited. And this one looks kind of slow up and down. They're moving at the same speed, But this one's going up and down very slowly, and this one's going quickly.
The reason light wouldn't hit you is because it has no matter, right?
Pardon me?
The reason light wouldn't hit you is because it doesn't have matter.
Yeah, light is not matter, that's part of why it's hard to think of it as a particle, because a particle would be matter, right? But yeah, it's not physically hitting you because it isn't matter. Yeah, it's energy.
For the first one, is it a high energy or low energy?
Thank you. I did that wrong. They can't both be high energy. This one was supposed to be low. I screwed up. Thank you. So this one's low energy, and this one's high energy. Any other questions?